In today's lecture, we will continue the thermodynamic models. So we finished all the parts related to the solids and liquids, and now we will start talk what if we have ideal gas. Last lecture, we explained what are the main characteristics of ideal gas. So we said ideal gas, it has no collisions between the molecules, no intermolecular forces. The volume between the molecules is very small. So what will be the relationship between enthalpy and internal energy for ideal gas? So again, the equation we have is enthalpy equal internal energy plus PV. This is the equation, the relationship between enthalpy, internal energy, and flow work. If we have ideal gas, then we have ideal gas equation of state. And what is the ideal gas equation of state? PV equal RT. So this term, PV, we can replace it with this term, RT. So we can say only for ideal gases, enthalpy is internal energy plus RT. Okay. And let's recall, in chapter 1 we said if you have internal energy, the value of this internal energy function of temperature, function of pressure, function of volume, function of the intermolecular forces. But if you have ideal gas, in previous lecture we said for ideal gases, we don't have any intermolecular forces. The interactions between the molecules are neglected. So this means the pressure and volume effect for ideal gases also is neglected. So if internal energy depends on pressure, temperature, volume, intermolecular interaction, but for ideal gases, the effect of pressure, volume, intermolecular interactions can be neglected. So what is remaining? Temperature, right? So this means if you have ideal gas, the value of the internal energy for this ideal gas or the value of the enthalpy for this ideal gas is function of only temperature. Okay? So again, so the first thing that you need to know about ideal gas, value of internal energy, value of enthalpy for ideal gases, function of only temperature. Only temperature can change the value. Changing pressure, changing volume, intermolecular interactions, their effect will not exist for ideal gases. Only internal energy and enthalpy is function of temperature. So if we make this relation, we have temperature at the x-axis, we have internal energy, we have enthalpy on the y-axis. So we have a straight line represent how the internal energy will change with temperature. Enthalpy is internal energy plus flow work. So always the value of enthalpy is more than the internal energy. Okay, so far it's clear? Any questions? Okay, so let's go back to the equations we have. In the previous lecture, we said the change of the internal energy, either molar or specific, as CVDT. Enthalpy, either molar is specific as CPDT. And again, CV and CP function of temperature. Then we can integrate this equation to say the change we have in the internal energy is integration of CVDT. The change we have in the enthalpy as integration of CPDT, and the relationship we have between, so what is the relation between CP and CV for ideal gas? For liquid and solid, they are equal. CP and CV are the same. But do you think in ideal gas, CP and CV will be the same? So the answer is no. There are some differences. Because already you have H is U plus RT for ideal gases. So what is the relation between them? So let's start from the end. For ideal gases, CP is CV plus R. So this is the relation we have. For liquid and solid, CP equals CV. Change in internal energy equally change in enthalpy. For ideal gas, CP is CV plus R. How we can end up with this equation? That's you. So if we start, again, we said for ideal gas, H is U plus RT. And we just said that DH is CPDT. Okay. So if you plot this one here, so you can say DH, which is DU plus RT, this one is equivalent to H from here, or sorry, from here. This one is CPDT. Start to distribute the derivative in these both terms, so we have DU plus DRT. R is constant, so we can take it out of the derivative form. And du, we know that du is CVDT, so du, this one will be CVDT. dRT, this one will be RDT, equivalent to this one. So again, du plus RT, this one is this term, We have du, this is Cv dt. We have dRt, this one is rdt. So if you can see this one, dt will be cancelled, and at the end, what you would have is Cp is the summation of Cv plus RT. Clear? So again, so in summary, we have internal energy, Cv dt. We have enthalpy, Cp dt. One of them, heat capacity at constant volume, another one, heat capacity at constant pressure. If you have liquid, if you have solid, Cp and Cv are the same. So any change in internal energy equal any change in enthalpy. For ideal gas, Cp equals Cv RT, Cv plus R. So the change in internal energy not equivalent to any change in the enthalpy for ideal gas. Any questions? Okay. This map here, this one will present all the equations we have in chapter 1 and chapter 2. Starting from the forms of energy. So if you remember, we have static forms of energy, dynamic forms of energy. Static forms of energy, kinetic, potential, internal. Dynamic, work, and heat. Heat, we have conduction, convection, radiation. These are the equations. You should know these equations from transport phenomena. If you are not familiar with them right now, this is fine. But these are the equations you can use to calculate Q based on the heat transfer mechanism. Work, we have three types: flow, shaft, expansion, contraction. Flow work plus internal energy together, here we have the enthalpy. Enthalpy is based on Cp value, internal energy based on Cv value. If you have liquid and solid, Cp and Cv are the same. If you have ideal gases, Cp is Cv plus R. Clear? So all the equations we have discussed so far in chapters 1 and 2 are represented in this one. You can take picture in this one. This is not in the slides you have. Let's see examples. So this examples, it says we have balloon. This balloon portion of a dirigible is filled with 5,000 moles of helium. So this moles have 5,000 moles of helium. Initially, this helium at pressure 1 atmosphere, 25 degrees Celsius. As this dirigible gains altitude, the pressure drops to 0.95 atmosphere, temperature drops to this one. Find the change we have in volume, internal energy, enthalpy for the helium in this process, assuming this helium has an ideal gas. So he says we can assume ideal gas behavior for this gas, and the heat capacity is 1.5 R. Okay. So we have at initial condition, number of moles, pressure, temperature. Final states, we have same number of moles, pressure, temperature. He said we need to assume ideal gas behavior, and we have the value of heat capacity. And we have three requirements. What will be the change we have in the volume, change we have in the internal energy, change we have in the enthalpy. Okay, so let's start the first one. So the first one we have here, he said we have ideal gas. So this means the ideal gas equation of the states, PV equal nRT. The initial condition we have so we have the pressure is 1 atmosphere. Number of moles is 5,000 moles. Temperature is 25 degrees Celsius, but we don't use Celsius, so this plus 273 to 98 Kelvin. Final conditions. So the pressure will be dropped, it will be 0.95 atmosphere. Number of moles will be the same, 5,000 moles. Temperature is 15 plus 273, so it will be 288 Kelvin. So these are the conditions we have. You can convert pressure from atmosphere to Pascal and use the R value 8.314. This is the R value in the SI unit. Or you can check, remember the slide that contains different values of R? So you can check one of them and you can see that we can use R value as 0.02 to 06 liter atmosphere per mole Kelvin. So this is value of R. You can use this value. If you will use this value, so the pressure must be in atmosphere, number of moles must be in mole, temperature in Kelvin, and the volume that you will be calculating, so this one will be in liter. So this is the units of the volume that we can obtain from this one. So you can substitute in this equation, one time with the initial condition, one time at the final condition. So if you will substitute this one, then the volume at the initial condition, this one will be 1, 2, 2, 3, 0, 0 liter. The volume at the final condition, so this one will be 1, 2, 4, 5, 0, 0 liter. And then he need to calculate the change. So delta V, which is V2 minus V1, this will be 2200 liter. And this is the first requirement. So this is the change in the volume that we have in the system. Clear? Second requirement, we need to calculate the change we have in the internal energy. This is what we need to find. So we know that the equation we have du is Cv dt. So by integration, this one then we have delta U is integration from T1 to T2 Cv dt. Cv is given in this example. So we have given that Cv is 3 over 2R. R, this is the ideal gas constant. 3 over 2, these are constant. So this means Cv is not function of temperature. Cv is constant. So why this is important? Because since Cv is constant, we can take out of the integration. So this one will be as Cv integration from T1 to T2 dt, or in other words, this one will be Cv T2 minus T1. Clear? Okay, then we need to substitute. Then we have Cv 3 over 2 or 8.314. This is the value of R in the SI system. T2 minus T1. So this one will be 15 minus 25. Delta T, you can calculate it in Celsius or in Kelvin. The value will be the same. Okay. So again, if you remember the value of R or the units of R, this one is joule per mole Kelvin. Here we have, this is the temperature, so this Kelvin or this temperature term will be cancelled, and the result we have, it will be joule per mole. So if you make this calculation, then you will have this negative 124.71 joule per mole. So now we calculate the change in the molar internal energy. Again, this is important. Is it required to calculate the change in the molar internal energy or in the internal energy itself? If you see the problem says we need to calculate the change in the internal energy, not molar internal energy. Okay, so from this one here we know that delta U molar internal energy is internal energy divided by number of moles. So this means the change we have in the internal energy is the change we have in the molar internal energy times number of moles. We calculated this one, which is negative 12471 times 5,000. This is the number of moles we have in the example. Then the change in the internal energy will be negative 623,550 joule. And this is the second requirement. Okay. Clear? So in the assignments or even in the exams, sometimes when I was giving an example and then I gave them the answer as a drop-down menu so they can select the answer. So you can find negative 124.71 in the menu we have, and you can find the correct answer, negative 62553. So again, make sure that what is required in the problem itself. Okay, make sure, is it the molar internal energy required or internal energy required? The values of these two parameters are different. And the difference is you account for the number of moles that we have in the example. Clear? Any questions? Okay. The last requirement we have here is the change in the enthalpy. So again, we know that the enthalpy equation, the H is Cp dt. We'll repeat the same calculations we have. So by integration, then we have delta H is the integration of the right side from T1 to T2 of Cp dt. The value of Cp is not given, right? But we know that Cv is there. We know that this substance is ideal gas. So for ideal gas, we know Cp is Cv plus R. So here, from this example, and based on the given we have, we know that this Cp value is Cv plus R. Cv is given 3 over 2R plus R. So this one will be 5 over 2R. So this is the Cp value we have. And this is the value that we will use to substitute in the equation. And again, R is ideal gas constant, so Cp is constant. We can take out of the integration term. So we can say this delta H is Cp integration from T1 to T2 dt, which will be Cp delta T, or Cp T2 minus T1. Now substitute the numbers we have here. So this one will be 5 over 2 or 8.314, T2 15 minus T1 25. So again, put all the numbers here and you can get the value. I don't calculate it, but anyway, then you can find the value of this delta H, and this will be joule per mole. And again, this is not the required. This is molar enthalpy. We need enthalpy. So we know that enthalpy is molar enthalpy times number of moles. Number of moles is given. This is 5,000. So we can substitute in this one, and the change in the enthalpy would be 1039,250 joule. And this is the requirement at the end. So far it's clear? Any questions? Okay. Now, what if the value of Cp or the value of Cv is not given? So here we have Appendix D. So again, if we go back to Appendix, remember Appendix A, this is the steam tables. Then if you finish this Appendix A, you will see Appendix B, which is related to some of the physical properties, I think, or mathematical derivations. Yeah. But Appendix B, this is just revision of some mathematical techniques. Then Appendix C, this is also important, this one for the physical properties. So this one for any substance, you can see the formula of this one. You can see the critical temperature, the critical pressure, the eccentric factor, we will explain this one later. Then the amount of heat needed for phase change between liquid and vapor, amount of heat required to change a phase from solid and liquid, and so on. Okay, so this is this importance of this appendix. Then we have appendix D. Appendix D, this one is for heat capacity. So this appendix tells you that if you need to find an equation to calculate CP, heat capacity at constant pressure, so CP divided by R is A plus BT plus CT squared DT cube AT to the power 4. A, B, C, D, E, these are parameters, and you can get these parameters from this like table. So these parameters specific for each substance. So let's assume if I have an example, and this example I have methane. So methane, the formula is CH4. This is the value of A for methane. Then I have negative 8.975. This is not the value of B. B times 10 to the power 3 equal this value. So B is this value divided by 1000. Then we have C times 10 to the power 5 equal 3.63. So what is the value of C? 3.63 divided by 10 to the power 5. We have D times 10 to the power 8 equal negative 3.4. So D itself is this number divided by the number we have here in the header of the column. Clear? So for any substance, you can get these parameters, substitute in this equation to get the value of CP. The last column here, this one represents T range. All of these parameters are like valid within a range. So you can use these parameters if the methane substance you have, its temperature between 50 Kelvin to 1000 Kelvin. Anything outside this range, then we have some uncertainty in using this equation. Okay? So let's get back to this example and see what we have here. So we have this example. Here the equation is given. These are the parameters we have. It says we have ideal gas heat capacity of nitrogen. So we have nitrogen. And this nitrogen behaves as an ideal gas. He said in the problem it behaves as an ideal gas. The CP of this equation, we have the CP equation equal all of this. See, this is all the value we have for CP. So you can see this is times 10 to the power negative 3, times 10 to the power negative 5, 10 to the power negative 8, 10 to the power negative 11. So these are parameters or the values we obtained from the appendix D, the appendix that we show right now. And he said that the value of CP based on this equation is in joule per mole Kelvin. Then he asks you how much internal energy per mole. So this one he needs molar internal energy. Okay, it's clearly said I need the internal energy per mole. What is the molar internal energy must be added to nitrogen to increase its temperature from this one to this one at low pressure. Then repeat this part if the temperature change from this value to this value. And then instead of using this equation given, assume that CP is constant and this is the value of CP, and repeat these two requirement A and B one more time. Okay, so what we will do in this one. So if we start solving this equation, again, we have ideal gas. This is requirement A. It says we have ideal gas. So again, this means the equation we have du as CV dt. Then do integration. Then we have delta U. This is what we need to find. The change we have in the molar internal energy is integration of CV dt from T1 to T2. So now the question, do you think CV is constant? Return this problem. So now, at first, we don't have any value of CV, right? But we have what? CP. CP, based on this formula, is constant or function of temperature? Function of temperature. So similarly, so the value of CV also will be function of temperature. So you cannot take CV out, similar to what we did in the previous example. So note that here we have CV is function of temperature. Okay. So again, what we have here, since we have ideal gas, so CV, this one will be CP minus R. So this is what we need to substitute. So substitute all the equations we have here. So then delta U, the change we have in this molar internal energy, equals integration from T1 to T2, and start to put CP value. So CP, this will be 29.42 minus 2.17 times 10 to the power negative 3 T plus 0.0582 times 10 to the power negative 5 T square minus 1.305 times 10 to the power negative 8 T cube, then minus 0.823 times 10 to the power 11 T to the power 4. This is CP. Again, this CP should be minus R. What is the value of R I should use? So again, in the problem here, he said CP in joule per mole Kelvin. So the value of R should have the same units. So the value of R that he will use will be minus 8.314. So this is the value of R you have. So now we have consistent. This, all of this we have now, this is CV. CP minus R. CP is given, we put the formula, the units of CP is joule per mole Kelvin, so we select R that match the units. So R is 8.314 joule per mole Kelvin. And all of this dt. Okay. Then what we should do, now we are ready for the integration. So then we can say delta U. So this one will be, you can note that all the parameters we have are multiplied by temperature except this one and this one. So you will calculate both of them together. So you can say, so delta U by integration, this will be 29.42 minus 8.314 T2 minus T1. So this is the integration of the first term. Then we need to integrate this term. Let's put it here. Now we need to integrate this one. So what you will do, we have here minus, so we'll put minus. Integration of T dt, if you remember, is T squared divided by 2. So this one will be 2.17 times 10 to the power 3 divided by 2 T 2 square minus T 1 square. So this, oops. So this one is the integration of this term. Then we need to go to the third term. Let's put it here. Now we need to integrate this one. Integration of T squared dt is T cubed divided by 3. You remember this math? Okay. Then we will do it. So we have plus, so this will be plus. You put the number 0.0582 times 10 to the power negative 5 over 3 T 2 cube minus T 1 cube. And this is the integration of the third term we have. Then next term, this one. This is T to the power 3, so T to the power 4 divided by 4. So this is minus 1.305 times 10 to the power negative 8 over 4 T2 to the power 4 minus T1 to the power 4. And this is the integration of this term. And the last term we have, this will be this term. So So this term here, if you integrate it, we have minus, so this will be minus, put the number 0.823 times 10 to the power negative 11 over 5 t2 to the power 5 minus t1 to the power 5. And this is the last term we have.
In between the green and the blue term, should that be a positive because of the initial equation? For the specific?
Okay, you mean this sign? Right?
Yes.
Okay.
Or that, because of the, yeah.
What's negative?
It's negative?
Yeah, so you see this is the original equation. We have negative, so I put negative.
In the problem statement, it's positive.
Really? Okay, so in the problem statement, like, right. So this is positive, this is positive. Yes.
Okay.
I just kept it wrong. Okay, right. So far it's clear? So this will be the equation that we can use to calculate delta U. Just we put CV, we make the integration. So now we see how the integration will be simple if CV is constant, not function of temperature, and how it will be like more complicated if CV is a function of temperature. So now requirement A says integrate this equation if T1 is 450 Kelvin, T2 is 500 Kelvin. It's just we need to put these numbers here. T2 is 500, T1 is 450, and if we put this, so now we need to substitute in this equation. T1 is 450, T2 is 500, then by substitution, then the change in the molar internal energy, this one will be 1059 joule per mole. This is the first requirement we have. Clear? Second requirement, B, use the same equation, but this time this will be the value of T1, this will be the value of T2. Now you can see T1 and T2 we have like large difference between requirement A and B. Requirement A, we have only 50 Kelvin. Requirement B, we have more than or almost 700 Kelvin difference. But we will repeat in the same equation. So again, requirement B, so again, sub in delta U equation with T1 is 273 Kelvin, T2 is 1073 Kelvin, then the change we have in the molar internal energy, so this one will be 17920 joule per mole. And the value is positive because we are increasing the temperature. Third requirement, he said, repeat the same calculations, but instead of using this long formula of CP, use only this one. CP is 7 over 2R. So in this requirement, he tell you assume that CP and CV are constants. So what will be the change we have? So again, for this requirement, he said CP is 7 over 2R. And we know that CP is CV plus R. So this means the value of CV is 5 over 2R. So the same equation, we have delta U. This one is integration from T1 to T2 CV dt. Now in this requirement, CV is constant. It's not function of temperature. Take it out of the integration. So this one will be CV T2 minus T1. We have the value of CV, T1 and T2, again for requirements, for this requirement. So let's repeat requirement A one more time. So if you calculate this requirement, so delta U, this one will be 5 over 2, 8.314, T2 minus T1, 500 minus 450. and this would be, let me get the number, this would be 1039 joule per mole. And if we repeat the same calculation for requirement B, so delta U is 5 over 2, 8.314, 1073 minus 273. So this one will be 16628 joule per mole. And this is the requirement we have. So what we need to get from this equation? So again, we calculated requirement A. The answer was 1059. Let's put it here. So requirement A, the answer of delta U is 1059 joule per mole. So let's try to compare the numbers we have here. So this is the requirement A. This is the change of the internal energy for requirement A. When you use CV, the actual CV value, which is function of temperature, this is the value of the change on the molar internal energy when we assume that CV is constant, is not function of temperature. These numbers are close, right? So this means if you have small temperature difference, you can assume that the value of CV is constant. Because if you use CV as constant or the formula of CV as function of temperature, the difference between the numbers will not be large. This is still acceptable. Okay? So again, for small temperature differences, you can assume that CV is function of temperature and simplify your mathematical equation. But on the other side, you can see here, when we use or calculate the requirement B, here we have 17,000, but here we have 16,000. We have large difference. So the assumption that of CV is constant, this is valid only for small temperature differences. But if you have large temperature differences, so this assumption may not be valid because the difference in the numbers will be huge. Since you can see here, more than 1,000 joule per mole is difference between the numbers we have. Clear? So again, for ideal gas, we know that Cp is Cv plus R. Cp and Cv, these are function of temperature. But as you can see, if we rely that on the function of temperature and we assume the actual formula for them, so the solution will be complex than if we are assuming they are constant. So when we can assume they are constant with confidence, if you need to calculate the change in internal energy or a change in enthalpy for small temperature like differences. But for large temperature differences, even if you have an ideal gas, then you should account for the dependency of temperature on the heat capacity value you have. Make sense? Clear?
There's a small asterisk next to the CP. Does that mean anything?
No, it just means it's in joule per mole Kelvin. Yeah, just indicate the units we have. Questions? Sure? Okay, we still have more examples. Do you have any energy? Stop here. Let's stop. Let's continue next lecture. See you next week. Enjoy the weekend.